Hello, this is Alex Benson, and I'm going to be doing a video today on the topic of heat capacity. It's chapter 20.2 in the book. So, this is a very cool topic of the book due to its highly interesting nature. And, what it states is, when energy is added to a system and there is no change in the kinetic or potential energy of the system, the temperature of the system usually rises. So, if the system consists of a sample of a substance, we find that the quantity of the energy required to raise the temperature of the given mass of the substance by some amount varies from one substance to another. By saying this, it's pretty much giving this equation right here, Q equals C, change of T, which from the definitions we see that energy, which is Q, produces a change of T, which is the temperature, and C is the specific heat, which can be given in, there's different specific heats for each substance we have. And with that, we go on to specific heat, which is heat capacity per unit mass. And specific heat, the equation is C equals Q over mass times change in temperature. Specific heat of a substance is the heat capacity per mass. And so if the energy transfers to a sample of a substance with mass m and the temperature of the sample changes by a change of T, the specific heat of the substance is this equation. So an example in the book given is to raise the temperature of water, 0.5 kilograms of water by 3 degrees Celsius, you plug it into this equation, and bada bing, bada boom, you get 0.5 kilograms times 4,186 joules per kilograms per Celsius, and that is the specific heat, which is given to us at a table, and then you multiply it by 3 degrees Celsius, and you get the answer of 6.28 times 10 to the third joules, and that is the energy required to raise the temperature of water, 0.5 kilograms of water by 3 degrees Celsius. So with this, we will head over to the problem, but first, I'm going to get a cheap laugh with using a Calvin and Hobbes strip. One of my favorite ones, of course. Alright, on to the next part, bigger and better things. So the problem. A combination of 0.25 kilograms of water at 20 degrees Celsius, 0.4 kilograms of aluminum at 26 degrees Celsius, and 0.1 kilograms of copper at 100 degrees Celsius are mixed in an insulated container and allowed to come to thermal equilibrium. Ignore any energy transfer to or from the container. What is the final temperature of the mixture? To start this, you use the Q equals C change of T. And so first we had to go look at the table and find the calculated specific heat for each one. For water, it's 4,186 degrees Celsius. Copper, 387. Aluminum, 900. Or not degrees Celsius, it's joules over kilograms degrees Celsius. Alright, so what you do is you plug into the equation and you get 100 degrees Celsius minus temperature final, that's the change of T, times the specific heat of copper times the mass of copper equals T final minus 20 degrees Celsius times specific heat of water times mass of water plus 20 degree T final minus 26 degrees Celsius, C of aluminum, mass of aluminum. And given the masses, mass of copper is 0.1 kilograms, mass of water 0.25, mass of aluminum is 0.4. And you just plug and chug, put it in the specific heats to the C's, and the masses to the masses, and then you solve for T of F, which you get is 23.6 degrees Celsius. So by plugging into the heat plugging into the heat capacity equation, we are able to solve for the energy it takes to change, or the final temperature of each of these, it takes for each of these substances to change to be the one temperature. And yeah, that's the summary of heat capacity. And yeah, just one more Calvin and Hobbes strip, I guess. Well, that'll do it.